Welcome back to the deep dive. Today we're really getting into the nuts and bolts of building your own cloud infrastructure.
That's right. There's this definite appeal to the do-it-yourself cloud, isn't
Oh, absolutely. That idea of total control, picking the absolute best components for every part of the stack.
it? Cherry-picking the best-in-class gear, avoiding vendor lock-in.
And starting fresh, no legacy baggage.
It sounds like the dream scenario for an architect.
It really does. But that freedom comes with a pretty hefty price tag in terms of responsibility.
That's a huge responsibility. When you go DIY, you are the integrator. You're the one making it all work together.
And the troubleshooter. There's no single vendor to call when things go sideways.
Exactly. The buck stops with you, the architect.
So we're tackling a key part of that today. We're looking at the instructional module, architecting a do-it-yourself solution.
And zeroing in specifically on compute considerations. This is really the foundation.
Right. If you don't get the compute layer right, the whole thing is built on shaky ground. We need to extract the practical wisdom here.
From selecting the actual servers all the way up to designing for things like scalability and security, it all starts with compute.
And just to remind everyone, the DIY model is about bringing together different pieces, servers, networks, storage, maybe from different vendors.
Yeah, the upside is you can bypass maybe old company policies, avoid existing bottlenecks, and really get that freedom from being locked into one ecosystem.
Which is huge for multi-cloud strategies down the road.
Definitely. But the trade-off is, well, it takes longer to implement.
And you need serious expertise on staff, people who really know how to make these disparate parts sing together.
That's often the biggest hurdle, actually, finding and retaining that talent.
So the architect has a ton of decisions to make. Let's start at the beginning, structuring the compute resources logically.
Okay, so the first concept is compute pools.
Right, and this isn't just about physical racks, is it? It's more abstract.
Exactly. It's a logical grouping. You group resources based on specific characteristics.
Like what kind of characteristics are we talking about?
Well, things like performance needs, maybe security levels, required availability, even physical location.
Or configuration differences, or maybe which tenant owns those resources in a multi-tenant setup.
Precisely. So this is your first big design choice.
Yeah.
How do you carve up your compute resources?
When would you ever just have one single pool? It seems like most environments would need more nuance.
You could use a single pool, but only if you're supporting a very generic workload.
Like everything gets the same treatment.
Yeah, basically a best effort policy for performance and availability across the board. Think small, maybe homogeneous setups.
Okay, but that breaks down pretty quickly if you have different needs, right? Like a critical database versus a dev test sandbox.
Instantly. The moment you need varying performance tiers or different availability guarantees.
Like tier 1 versus tier 3 support.
Or specific security postures, like for PCI compliance or maybe a DMZ.
Then you absolutely need multiple pools.
You have to. You need to segregate those resources logically so you can apply the right policies, the right management, the right SLAs to each specific group.
And what's the key advice for making these pools manageable operationally?
Consistency. Within any single pool, keep the server design consistent.
Same processor, same RAM, same I/O cards, everything.
Ideally, yes. It makes moving VMs around so much easier. Support becomes simpler. Lifecycle management is streamlined.
Avoids those weird troubleshooting scenarios where one host behaves differently.
Exactly. Inconsistency just creates headaches down the road.
Okay, that makes sense. So moving from the logical pool to the actual hardware, physical server selection.
Ah, the classic debate. Blade versus rack servers.
Where do you start with that decision?
It's a fundamental choice impacting density, cost, potential lock-in, flexibility, lots of things.
So blade servers first. What's the main draw?
Density. High-density computing. They pack a lot of compute power into a small physical footprint because they share components.
Like networking, storage connectivity, power within the chassis.
Right. It's integrated, which is great for space efficiency.
But there's always a but, isn't there? What are the downsides?
Two main ones, usually. First, they often have limited space for internal disk drives.
Which makes them less ideal if you need lots of local storage.
Correct, especially if you're thinking about things like software-defined storage down the line.
And the second drawback.
This is a big one. Potential vendor lock-in. The blade chassis itself is proprietary.
You're buying into that vendor's specific backplane, their management tools, their I/O modules.
Exactly. Once you're invested in a particular blade system, getting out of that ecosystem is, well, difficult and usually very expensive.
Okay, so contrasting that with the traditional rack servers?
Rack servers are sort of the default workhorse. Their big advantage is flexibility, especially with local storage.
More room for disks inside the box.
Much more, which makes them a natural fit if your design includes software-defined storage, SDS.
Or if you're maybe planning for hyper-converged infrastructure, HCI, later on.
Absolutely. HCI relies heavily on those high-capacity local drives. Rack servers give you that option.
Now, let's talk cost trade-offs, because it's not always straightforward.
No, it really isn't. You look at the base, just the box, CPU, RAM, and often two smaller servers look cheaper than one big one.
That seems like a win for scaling out with smaller units.
It seems like it. But you have to factor in all the input-output cards, the NICs, the HBAs.
And the redundancy needed for each of those cards, right?
Precisely. For high availability, you need redundant network connections, maybe redundant fiber channel connections via HBAs.
Or maybe specialized cluster area network cards, CANs, for things like clustering traffic.
Right. So if you choose two smaller servers instead of one larger one, you've just doubled the number of physical I/O cards you need to buy.
And doubled the number of switch ports you need to connect them to.
Exactly. Suddenly, those base cost savings can evaporate pretty quickly when you factor in the total connectivity cost.
That's a really important hidden cost. And that leads right into licensing implications.
Oh, licensing. This can totally change the equation.
How so?
Well, many hypervisors are licensed per physical host or sometimes per socket.
So if you use larger servers and consolidate more VMs onto fewer physical boxes,
Your licensing costs can drop dramatically. Fewer hosts means fewer licenses to buy and maintain.
you also need to check the fine print, right? Does the license depend on processor type or core count or maybe memory limits?
Absolutely. You have to read the licensing agreement very carefully. It's not always just about the number of servers.
And beyond the upfront CapEx for licenses, consolidating onto larger servers impacts the ongoing costs too, the OpEx.
Big time. Fewer, larger servers mean less physical space used in the data center.
Fewer power connections, less cooling required.
Lower electricity bills every month, less maintenance complexity. It all adds up to significant OpEx savings over the life of the hardware.
Okay, hardware selected, form factor decided. Now we need the software virtualization layer, hypervisor server selection.
And first, let's be clear. Technically, you don't need a hypervisor for cloud.
You could just use containers on a base OS.
Right. But for efficiency, for sharing resources effectively, for scaling quickly, and for controlling costs, almost all enterprise DIY clouds use a hypervisor.
It's the standard approach for a reason. So when you're choosing that hypervisor, what are the key things the architect must consider? Let's say top 5.
Okay, number 1, absolutely critical, underlying physical component support.
Does it actually work with the hardware you just picked?
Yes. Does it have the right drivers, the right plugins, certified support for your specific network cards, your storage adapters, your storage arrays, even the processor architecture?
If that compatibility isn't solid, you're asking for trouble.
Massive instability, performance issues, yeah. It has to be certified.
Okay, number 2.
Licensing cost, the Eternal Balancing Act.
Proprietary versus open source.
Essentially. Proprietary hypervisors often have rich feature sets and strong vendor support, but they come with license fees and ongoing maintenance costs.
Whereas open source options eliminate the license fee.
But might require more in-house expertise, or you might end up paying for third-party support contracts anyway. It's a total cost of ownership calculation.
Got it. Number 3, how does it play with the bigger picture?
CMP compatibility. Your cloud management platform, the thing orchestrating everything, needs to talk to the hypervisor seamlessly.
Not all CMPs support all hypervisors equally well.
Definitely not. Some integrations might be basic, or you might need extra software shims like element managers just to get the CMP to properly manage the VMs or hosts. You want native, deep integration if possible.
Makes sense. What about features within the hypervisor itself? Number 4.
Look for native advanced features, things built right into the hypervisor platform.
Like what?
Host clustering for high availability, that's huge. Automatic load balancing or resource distribution. Advanced memory management features like ballooning or compression. Maybe built-in network or storage traffic shaping.
Using native features is usually simpler than bolting on third-party tools later.
Generally, yes. It leads to a cleaner, more integrated design.
Okay, and the 5th factor. This one feels less technical, but maybe more impactful sometimes.
Oh, it often is. It's organizational expertise.
What does the team already know?
Exactly. If your IT staff has years, maybe decades, of experience with hypervisor vendor X, suggesting a switch to vendor Y even if Y is technically better on paper.
That's a tough sell. You're looking at significant costs for training, retooling, probably expensive support contracts during the learning curve.
Right? The inertia of existing skills and vendor relationships is a powerful force in IT architecture. It often overrides pure technical merit. It's the human element.
So given all that, sometimes the answer isn't one hypervisor, but multiple hypervisor selections. Why add that complexity?
It usually comes down to unavoidable technical requirements or integration needs.
Like what? Maybe one hypervisor doesn't support a critical legacy OS.
That's a common one. Or maybe peak performance for a very specific, crucial application demands a particular hypervisor it's optimized for.
Or connecting to external clouds.
Yeah, hybrid cloud scenarios. If your strategy involved connecting to a specific public cloud provider, you might need to run a compatible hypervisor internally for seamless workload migration.
But wow, the downside seems significant. You really need a good reason.
You absolutely do. The drawbacks are serious. First, management complexity just explodes.
Multiple consoles, multiple tool sets, different ways of doing things.
Exactly. Admins need to learn and manage multiple systems, multiple sets of procedures, multiple configuration standards. The risk of human error goes way up.
And what about keeping things running? Recovery.
That's the second point, recovery complexity. Your disaster recovery planning gets much harder. Each hypervisor platform has its own HA and DR mechanisms.
So you basically have two or more separate recovery plans to design, test, and maintain.
Pretty much. They don't usually integrate at that level. Third, resource allocation becomes inefficient.
How so?
With a single hypervisor, you can treat your entire compute capacity as one large pool. Resources can be shifted easily. With multiple hypervisors, your resources are siloed.
Harder to borrow capacity from the VMware pool if the Hyper-V pool is running hot.
Exactly. You lose that overall resource pooling efficiency.
And the final nail, operational cost.
Generally, yeah. While the initial purchase cost might vary, the day-to-day operational costs, OpEx, are usually lower with a single standardized hypervisor. Less training, simpler support, unified maintenance. Less effort just keeping the lights on.
Okay, one more foundational choice before we get into sizing. Container selection. For organizations bypassing hypervisors for some workloads.
Right, running applications directly on a base OS, using containers for isolation without the hypervisor overhead.
What are the key considerations here? Similar to hypervisors.
Some are similar, some are unique to containers. First, you still need base OS compatibility.
The underlying host operating system still needs the right drivers for the network cards, storage, processors, etc.
Correct. That fundamental hardware compatibility is always step one.
But then there's a core difference in how containers work.
This is the crucial one. Container and OS kernel sharing. This is what makes containers lightweight. They share the kernel of the host OS.
Unlike VMs, which each have their own full OS and kernel.
Exactly. So the container management platform needs to support the host OS, obviously. But the big limitation is if an application requires a different OS kernel.
Like a Windows app on a Linux host?
It simply won't run. All containers on a host are tied to that host's kernel type. That limits your flexibility compared to VMs.
What about managing containers through the cloud platform?
That's number 3, CMP integration.
Yeah.
Many CMPs were built primarily for VMs. Native container management might be limited or non-existent.
So you might need extra tools.
Often, yes. You might need separate element managers or specific container orchestration platforms like Kubernetes, and then figure out how to integrate that with your main CMP for visibility and lifecycle management. It can add layers of complexity.
And finally, what about adding features like high availability to containers?
Good point. That's advanced feature overheads. Unlike hypervisors that often have HA built in, adding things like clustering, service meshes, or enhanced security to containers usually means installing additional software layers on the host OS.
More agents, more daemons running alongside the containers.
And those extra processes consume CPU and memory on the host. So when you're sizing your container hosts, you have to account for the overhead of the container runtime, plus all these extra management and feature applications.
All right, we've picked our foundation servers, hypervisor, or containers. Now we get into the math. Capacity design strategies.
This is where the rubber meets the road, turning requirements into an actual hardware order. You can't just guess.
What information does the architect absolutely need before they can even start sizing?
You need specifics. What services are we running? How many? What's the architecture of each service? What are their OS and application resource needs?
And critically, how are they actually going to be used?
Usage patterns. Yes. If you have existing similar services, you need monitoring data. Real data, not just guesses. Average use, peak use, cyclical patterns.
You need that baseline and the main factors that will influence the final server count and specs.
It boils down to processor needs, memory needs, the sheer number of VMs or containers you have to support.
Plus your high availability requirements. Do you need N+1 redundancy?
Right, and any security requirements that might force you to dedicate resources, which impacts overall utilization.
Okay, let's get into the detailed sizing exercises. This is crucial. Let's use that example. Needing to support 200 VMs.
We'll start with processor sizing. And the big factor here is the oversubscription ratio you're comfortable with.
How many virtual CPUs, vCPUs, are you assigning per physical CPU core?
Exactly. So for our example, let's say each server has 2 physical processors. Each processor has 8 cores. We'll aim for a 2.1 oversubscription ratio.
Meaning 2 vCPUs per physical core.
Right. And we'll assume hyperthreading is enabled, giving us a hyperthreading value of 2.
Okay, walk us through the calculation. Step 1, total physical cores needed.
Okay, so the formula is total VMs divided by the hyperthreading value, then divided by the oversubscription ratio.
So 200 VMs divided by 2 for hyperthreading
Is 100. Then divide that by 2 for our oversubscription ratio.
gives us 50. We need 50 physical cores total across the whole environment.
Correct. That's the effective number of cores required to support those 200 VMs at our target efficiency.
Step 2. How many physical processors does that translate to?
We take the total cores needed, 50, and divide by the cores per processor, 8.
50 divided by 8 is 6.25.
Right, and since you can't buy a quarter of a processor, you round up. We need 7 physical processors.
Okay, final step. How many servers?
Total processors needed 7, divided by the processors per server, 2.
7 divided by 2 is 3.5.
Round up again. We need 4 physical servers to meet the CPU demand based on these inputs.
See, that systematic approach gives you a concrete number, not just a guess. Now, memory sizing for those 4 servers.
Memory is often less about oversubscription and more about overhead. Let's assume our inputs are: each VM needs 4 gigabytes of RAM.
And we'll be conservative here, no RAM oversubscription, so a 1.1 ratio.
Good. We also need to account for the hypervisor or host OS itself. Let's say 512 millibeat per server.
And some general overhead for management agents, maybe future growth buffer.
Yeah, let's add 2 gigabytes per server for that overhead.
Okay, calculation time. First, how many VMs are on each server?
Simple division. Total VMs, 200 divided by total servers, 4 equals 50 VMs per server.
Got it. Now the memory formula per server.
And it's RAM per VM multiplied by VMs per server divided by the oversubscription ratio plus the OS RAM plus the overhead size.
Okay, plug in the numbers.
So 4 gigabit RAM VM, 50 VM server 1 for oversubscription, plus 0.5 gigabit OS RAM, plus 2 gigabit overhead.
That's 201 plus 0.5 plus 2 equals 202.5 gigabit.
Right. And again, you typically round that up slightly for safety or standard DIMM sizes, maybe to 2 to 3 gigabits, or more likely to the next standard server config like 256 gigabits.
The key takeaway here seems to be how much leverage that oversubscription ratio gives the architect, especially for CPU.
It's massive. Getting that ratio right is critical. Be too conservative, and you buy way too much hardware. Be too aggressive.
And performance tanks. What's a reasonable starting point for vCPU to physical core ratio?
General guidance is often around 4.1 as acceptable for many workloads, pushing to 6.1 or 8.1.
You start risking significant contention, right? VMs waiting for CPU time.
Exactly. Does it show up as a crash, usually? It manifests as slowness, latency, applications hanging intermittently.
Yeah.
Users just feel like things are sluggish.
So monitoring is key after deployment.
Absolutely critical.
Yeah.
You need to watch CPU ready time or equivalent metrics.
Yeah.
If a VM is consistently using its allocated CPU, maybe it needs another vCPU, or maybe the pools ratio needs adjustment.
Okay, capacity is calculated. Now, availability design strategies, making sure it stays up.
Because in DIY, availability isn't just bought, it's designed and built. It's the system's ability to function as needed, when needed.
Depends on component reliability and making sure you can always get to the data.
Right. Simple calculation is uptime divided by total time. Like 999 hours up out of 1,000 is 99.9% available.
What's rule number 1 for designing high availability?
Eliminate single points of failure, SPOFs, everywhere.
Compute, network, storage, the whole stack.
The whole stack. For compute hosts, dual power supplies plugged into different circuits, redundant network cards connected to different switches, maybe mirrored boot drives, multiple paths to storage through different switches and HBAs.
You have to assume components will fail and design around it?
That's the mindset.
Mm.
And the core strategy, specifically for compute HA, is clustering.
Grouping servers together so if one dies, the others can take over.
Exactly, grouping redundant compute nodes. But there are different ways to implement clustering. The main two are active-active and active-passive.
Let's break those down. Active-active.
All nodes in the cluster are running the service simultaneously. Workload is spread across them.
The benefit is potentially higher performance during normal operation.
Potentially double the performance, yeah. And failover is usually instantaneous because another node is already running the service.
That's the catch.
You must leave enough spare capacity on the surviving nodes to handle the load of a failed node.
So you're intentionally buying hardware that sits partially idle just for failover? That seems inefficient for DIY cloud.
It is, from a pure utilization standpoint. That's the trade-off. You pay more in CapEx and OpEx, powering, cooling that spare capacity for that instant, zero downtime failover. It increases your KTLO, keeping the lights on costs.
Okay, so what about active-passive?
Here, you have one or more active nodes running the service and one or more passive nodes just sitting there, waiting.
Like a standby server.
Exactly. If an active node fails, the service fails over and starts up on a passive node.
The benefit is better resource utilization day to day.
Yes, you're not paying to power idle capacity quite as much. The downside is.
There's usually a brief outage during the failover, right? While the service restarts on the passive node?
Correct. It might be seconds, it might be a minute, depending on the application. So the choice between AA and AP really depends on how much downtime the specific service can tolerate.
And finally, leveraging the hypervisor itself for HA.
Most modern enterprise hypervisors have built-in hypervisor high availability. Think VMware HA, Hyper-V failover clustering.
What does that do?
It monitors the physical hosts. If a host fails, crashes, loses power, network isolation, the hypervisor automatically restarts that host's VMs on other healthy hosts in the cluster.
So it provides automatic recovery at the VM level?
Yes, it's a fundamental part of compute resilience in most virtualized environments.
Okay, we've got capacity, we've got availability plan. Now let's hit those key quality attributes: security, performance, and scalability, starting with security design strategies.
And security is paramount in cloud, especially DIY. The shared nature, the need for broad network access, it makes it inherently more vulnerable than traditional isolated systems.
And in DIY, there's no provider handling the base security. It's all on the architect.
Absolutely. You have to build it in from the ground up. First consideration, physical separation of hosts.
Actually putting certain workloads on entirely different physical servers.
Sometimes, yes. Compliance regulations like IDPA or PCI DSS might mandate it. Or you might want physical isolation for your DMZ, separating public-facing servers from internal ones.
So your design might need dedicated compute pools just for security zones.
It might. You might even use different types of infrastructure, maybe hardened enterprise gear for critical internal systems, and more commodity hardware for less sensitive cloud-native apps in the DMZ. Security requirements can drive hardware diversity.
Okay, what about protecting the management layer? That seems like a key attack vector.
It absolutely is. Securing host management interfaces is critical. These are the connections admins use to configure, patch, and manage the hosts.
Needs to be separate from the regular data traffic.
Ideally, yes. Physically separate networks, or, at minimum, logically separated using dedicated VLANs. And all that management traffic must be encrypted.
What about authentication for administrators?
Use a separate authentication system if possible, maybe leveraging a dedicated PKI for certificates. And enforce the principle of least privilege rigorously. Admin accounts should only have the permissions they absolutely need. A compromised admin account is disastrous.
And keeping the hosts themselves secure, software-wise.
That's host software hardening. It's a continuous process.
Patching, antivirus, minimizing services.
All of that. Consistent, timely patching. Keeping endpoint security tools, AV, IDSS, up to date. Applying security configuration baselines, turning off unnecessary services, hardening SSH configurations, etc.
And in a DIY environment with potentially different server types, consistency is key here too.
Mandatory. You need configuration management tools, Ansible, Chef, Puppet, SaltStack, to enforce these hardening standards consistently across every single host. Manual configuration leads to drift and security gaps.
Finally, how do you know if something bad has happened?
Host logging. Comprehensive logging is essential. Enable detailed logs on every host.
Access logs, errors, security events.
Everything relevant. But don't just leave the logs on the hosts. You need a central logging system, a SIEM or similar tool to collect logs from all hosts.
Why centralize?
For correlation, analysis, alerting, and auditing. If an attacker compromises a host, one of the first things they might do is try to delete the local logs. Centralized logging makes that much harder. It's crucial for troubleshooting, security investigations, and proving compliance.
Without logs, you're flying blind. Okay, let's shift to performance design strategies. How do you ensure the cloud feels fast and consistent?
Performance isn't just about raw speed, it's about predictability. Key strategies include using that consistent server hardware we talked about,
Right, avoiding performance variations between hosts.
ensuring everything is interoperable, applying network QoS policies where needed, minimizing network latency or hop counts. But two compute-specific points stand out.
First, that consistency again.
Yes, physical server consistency is huge for performance. Same CPU family and speed, same memory speed and configuration, same firmware versions on servers and adapters.
Why is firmware so important?
Minor firmware differences, especially on NICs or HBAs, can lead to significant performance variations or even compatibility issues, like problems with VM live migration. Consistent hardware gives you a predictable performance baseline and simplifies troubleshooting immensely.
And the second point, making sure things work together.
Interoperability. This is the heart of the DIY challenge. Every piece of hardware and software needs to be certified or verified to work together.
Checking vendor hardware compatibility lists, HCLs.
Absolutely. Is the hypervisor certified for this server model? Do the NIC drivers work properly with the hypervisor version and the CMP? Does the storage array integration function as expected?
If components don't integrate smoothly, performance suffers.
Or things just plain don't work? The architect has to verify every link in that chain. You can't assume compatibility.
Okay, final quality attribute. Scalability design strategies. Making the cloud grow gracefully.
The goal is to make the cloud appear to have limitless resources, even though we know the physical hardware is finite.
But buying and installing new servers takes time.
Yes, exactly. Procurement, shipping, racking, configuration, it's not instant. So the core strategy has to be proactive monitoring.
Watching resource usage trends.
Constantly. You need good monitoring tools, tracking CPU, memory, storage I/O, network bandwidth usage at the pool and host level. You need to see consumption trends before you hit capacity limits.
So you can start the procurement process early.
Right. If you know Pool A typically grows by 10% a month, and it's currently at 70% utilization, you need to order more servers now, not when it hits 95%. That monitoring gives you the necessary lead time.
When you do need to add capacity, there are two main ways, right? Scale up versus scale out.
Correct. Option 1, scale up, vertical.
This is adding resources to existing servers. More RAM, faster CPUs.
Yes, beefing up the individual boxes. But this is often less ideal for cloud environments.
Why is that?
It's usually a manual process. You often need to take the server offline, physically open it up, install the new components. That means downtime and careful planning to migrate workloads off first. Doesn't scale smoothly or quickly.
So it's usually reserved for specific, maybe monolithic applications?
Typically, yes. Or maybe very large database servers. The preferred cloud method is
Option 2, scale out, horizontal.
adding more servers to the pool, just like the existing ones.
And this relies heavily on that standardization we keep talking about.
Absolutely. You need that fully documented standard server build. When you add a new server, it has the same performance characteristics, the same configuration as all the others in the pool.
So the CMP can just seamlessly incorporate it into the available resources.
Exactly. And this is where automation shines.
Using orchestration and configuration management tools.
You bet. You shouldn't be manually building these new servers. Tools should deploy the OS, install a hypervisor, configure the networking and storage, join it to the cluster, all automatically and consistently.
Makes scaling much faster and less error-prone.
Orders of magnitude faster. And if you need a lot more capacity or different types of capacity, you can scale out by adding entire new pools as long as they also have well-defined, predictable characteristics.
Okay, that really covers a spectrum of compute considerations from logical design through physical selection, sizing, availability, security, performance, and scaling. #tag outro. So we've really unpacked the architect's job when it comes to the compute layer in a DIY cloud. It starts with those logical pools driven by SLAs.
Then navigating the hardware choices, blades versus racks, wrestling with density, cost, and that tricky vendor lock-in.
We dove into the actual math, how oversubscription ratios and memory overhead directly impact your server count and your budget.
And looked at building resilience through clustering, eliminating single points of failure.
Plus, layering on those essential qualities. Security hardening from the host up, ensuring consistent performance through standardization and interoperability.
And planning for growth with proactive monitoring and efficient scale-out strategies.
The key theme seems to be that in DIY, the architect owns every single detail of this compute layer.
That's exactly right. Success isn't just about buying fast hardware. It's about meticulous end-to-end planning for consistency, resilience, integration, and growth, from the silicon all the way up to the logical service delivery.
It demands a tremendous amount of foresight, detailed work, and frankly, deep internal expertise to pull off successfully.
It really does. Which brings us to a final thought, maybe a provocative question for you, our listeners, to mull over.
Yeah, drawing back to that initial allure of DIY freedom versus the complexity we've just spent time detailing.
Right. Given the sheer level of detail involved, the specialized staff knowledge required, the effort needed to calculate things like core counts and memory needs, to design specific security policies to manage interoperability.
All that heavy lifting we just discussed.
Does that inherent flexibility of the do-it-yourself approach
Yeah.
still genuinely outweigh the potential cost savings and operational simplicity you might get from pre-integrated solutions?
Yeah.
Things like converged infrastructure or hyper-converged infrastructure?
Where the vendor has done a lot of that integration and validation work for you.
Exactly. That's the fundamental strategic decision, isn't it? Balancing ultimate control and customization against simplicity and potentially faster deployment. It's the decision that really shapes the whole project.
Something definitely worth thinking about. Thank you for sharing all that source material and joining us for this deep dive into DIY compute.
Always a pleasure.
We'll catch you next time on The Deep Dive.